Hi everyone, this is a sample teaching. The topic that I've chosen is statistics hypothesis testing. My name is Fatemeh Asghari-Nejad. I'm a fifth year PhD candidate at EC Department of UC San Diego. And thank you so much for listening to me. Okay, in an actual classroom, what I will start with is announcements about if there's any homework due, any exam due, etc. I will have the lectures, discussion, office hours, everything here, and also all of the websites and whatever tools we are working with, so that students have access to all of them at one place. And then this is the course plan for the whole course. This is from the course I taught at CSE at UCSD this summer. So I would like to show where we are in this course. For instance, we are in week 3, lecture 10. So this is today's learning goals, and I assume that I'm teaching to an actual classroom. So today's learning goals are, first we will have a very brief review of statistics. Then we will start with how to use a statistics to evaluate some hypotheses about a population, which is called hypothesis testing. So for that, we will go over what is a hypothesis, what are null and alternative hypotheses, what are test statistics, type 1 error, and then we will learn how to accept or reject null hypotheses, and we'll go over p-value. Okay, so this slide should have been seen in the previous lectures, of course, which is the difference between statistics and probability. So if you have all of the information about the balls in a pail, then, for instance, you know that there are like 20 black, 10 white, and then 15 gray balls in the pail. It would be easy to calculate how probable it is to get, for instance, 2 black ones and 3 gray ones, right? So this is the kind of application um, we would use probability for. Or if I want to give you another example, you can think about, I do have the information about a whole population of United States people, about their height, for instance, and this is the average. Let's say it is 5 feet 8 inches. And then it would be very easy for me to calculate how probable it is for a person to be between like 6 and 6'1", right? I can just calculate what is this area. So this is when you have the information about the whole population, use probability to estimate how probable it is to get a sample from that. But a statistics is used when you don't have the information about the whole population. What you have is that you have information about a sample of that population. For instance, here you don't know what is in the pail. You only have got like 3 black ones, 1 gray one, and 3 whites. And based on the information you got from the sample, you are gonna guess and estimate some properties of the whole population. For instance, let's say in the example that we had here, you can say that I have the height of people to be 5 feet, like I have height of 100 people, 5 feet, 6 feet, 6, etc., etc. And based on these 100 or 1,000, I'm gonna guess what is like the average height in the whole US population. So those kind of applications you get from a sample to a whole population is in a statistics. And obviously you cannot guarantee with 100%. You cannot say, okay, based on this, I can say the average here is like 5'9", so that would also hold true for the whole population. No, but that's a good estimate. Okay. So one of the main practical use cases of a statistics is predicting which of the USA presidency candidates will win the election. Let's say this is before the election take place. So we want to estimate who's going to win the election. we ask a sample of the population of the United States people and estimate which candidate is likely to win based on their opinions. Some people might say President Trump will earn more electoral votes, therefore he will win. And some people might say former Vice President Harris will earn more votes. So we get a sample, let's say 100,000 people or whatever we can, and based on the information we get there, we can get a good estimate about who is more probable to win the election. So each of these two ideas, these two assumptions that President Trump will win or former Vice President Harris will win is called a hypothesis. A hypothesis is an assumption, a statement about parameters of a population or distribution that can be true or not true. So, and then as a reminder, a parameter is a numerical or measurable characteristic of a population, for instance, average, variance, mean, max, range, etc. So this is, I would like to have a lot of discussions in the classroom. So I would like to ask people in the class to discuss other real life hypotheses with your friends who are sitting close by. And I'll give them a few minutes. And in real world, I would like to write a lot on the blackboard to work with chunks. So I just use the slides as a review. But here, the format is different, so I'm just using the slides. Okay, once the discussion is over, I'm gonna write down the suggestions from students. We might get these. If we have a collection of individuals, we can hypothesize that the average height of Americans is more than 5'8" inches. Or some other students might say we can have an assumption that the average GPA of first-year students is more than 3.0. Some might say we can hypothesize that men play more video games than women, or we have a coin, and our hypothesis is that it is unbiased. So probability of heads is equal to probability of tails, and it's equal to 1. Okay, so another really main use case of statistics is when you want to estimate whether medicine will work or not. So as you see, statistics has very real applications in real life. And it's not just you study computer science, you need to know that. Many people in many different areas of studies are using the notions we are covering here in statistics. So, so let's say that a pharmaceutical company wants to evaluate the effectiveness of a medicine on a group of patients. So the population here we are discussing is patients. They are using a randomized clinical trial. Let's say that it is also ethical and people know what's going on. We are just discussing the mathematical side of it. So we give the actual medicine to half of the participants while the other half receive a placebo. And what is a placebo? It's an unreal medicine. Let's say acetaminophen, something like that, right? It's not a real medicine, but the participants know that half of them are given placebo, half are given actual medicine. Let's say that we have 6 people who took the medicine, we have 6 people who took the placebo. Okay, so there are 2 hypotheses here. One hypothesis is that there will not be any difference between 2 groups. So medicine is not going to be impactful. So what it means is that after they use the medicine, there won't be any differences between what happens to the patients in the 2 groups. So that's one hypothesis, right? Which is not what the pharmaceutical company wants. And the other one is that there will be a difference between 2 groups of people. So for instance, more people will be cured in the group who took the medicine, or symptoms will improve in the group who took the medicine, which is what the pharmaceutical company wants. So the assumption that is often believed to be true is null hypothesis. It often refers to the first one that says there won't be any difference between 2 groups. That is called null hypothesis. It's shown with H sub 0. And the often complementary of that view is called alternative hypothesis, which is shown with H sub A or H sub 1. And here the hypothesis that more people will be cured in the group who took the medicine are alternative hypotheses. Okay, so I hope it is clear what is a null hypothesis and what is an alternative hypothesis. And the alternative hypothesis is not always exactly complementary of the null hypothesis, but they are not the same as well, right? We'll see more examples. Okay. Now, I would like to ask the students to discuss the null and hypothesis and alternative hypotheses in real life scenarios. Okay, so let's say students are answering this. And so one null hypothesis could be men play more video games than women. And the alternative hypothesis of that, A sub A, is women play more video games than men, right? And you can see that it's not exactly complementary of H0, right? Or it could be women play equal amount of video games compared to men, right? It's not complementary again. The other example is people like rock and pop music equally. The alternative hypothesis of that could be more than 50% of people prefer rock music over pop. The other hypothesis we could have is that the coin that is used by a judge in a soccer game is unbiased, so probability of heads and tails is equal to 1/2. The alternative hypothesis of that is that the coin is biased, so the probability of heads and tails is not equal to 1/2. Okay, if there are no questions, we can move to the next slide. Okay, so in this scenario where we gave two groups of people, medicine and placebo, and we had two hypotheses about whether the medicine will be effective or not. What we do is we collect data. So we collect like how many people have been cured or something like that to measure whether the medicine have been impactful or not. And then after collecting the data, if the data is consistent with the null hypothesis, we would accept the null hypothesis H0. Otherwise, if you have a strong evidence for the alternative hypothesis, we reject the null hypothesis in favor of the alternative hypothesis, right? Okay. So, and then the whole act of doing that is called hypothesis testing. So, which characteristics should be studied to measure the medicine's impact? Can you think about some? So let's say that after 1 month, I want to measure whether the medicine have been impactful or not. What should I measure? As you mentioned, we could consider a very specific criteria, some symptoms, blood pressure, some very domain-specific things that we want to see whether they have been improved or not. Or in general, let's say that we want to see how many people have been cured or not. That could be also something, right? So let's say that we observe that 4 people have been cured out of 6 people in the group of people who took the medicine, and 2 have not been cured. But in the group that took the placebo, 1 out of 6 only have been cured and 5 have not been cured. So when you think about it intuitively, it seems that the medicine could work, right? So first of all, being cured or not cured, why did I even ask this question? Because we want to identify some measurable factors for evaluating the medicine's effectiveness, right? So all of the things you mentioned, the number of people being cured, the number of people who have the improved symptoms and all that, is called test statistics. Test statistics is a function, could be mean, standard deviation, count, ratio, etc., that helps us determine whether we should reject the null hypothesis or not. So here, as you have seen, it can be the number of cured people in a group, right? So after observing all these results, after 1 month, let's say, after the experiments is done, should we allow the pharmaceutical company to release the medicine? And should we set a threshold for rejecting the null hypothesis? The medicine is not effective. So for instance, what would happen? What would be the side if 3 people have been cured, 3 not cured? And here we had like 2 people being cured and 5 not cured, right? Would the things be different? Would our certainty about the medicine being impactful be changed, or would we be more certain about its effectiveness if 5 people got cured here and 1 not, and here 0 cured and 6 not? Right? Is there a threshold here? We are gonna answer this question. Okay, so we actually set a threshold. We cannot say, as you have seen in the polls, in the medicines, everything that are released, you do not see that they say with 100% confidence we can say that this is going to be effective. They usually say it with 99%, 95%, something like that. So we set a threshold for test statistics here, the number of cured people to reject H0 with some confidence. The confidence is called is denoted as 1 minus alpha, where alpha is significance level. So confidence is often set to be 99 or 95%. It could be different values as well. So when it is 99, it means that alpha, our significance value, is equal to 1%. And when it is equal to 95%, it means that our alpha is equal to 5%. So significance level is the probability of mistakenly rejecting H0 when it is actually true. Here, the medicine is not impactful. So it is actually, at most, the probability of mistakenly rejecting H0. And we'll see an equation that shows this. So what can we say about a large and a small value of probability of mistakenly rejecting H0 based on test statistics, given that H0 holds true? This is a conditional probability, right? We already know that H0 is true. So we want to know what is the probability that we mistakenly reject H0. What can we say about it? You can discuss this. So when H0, when probability of mistakenly rejecting H0 is given that H0 holds true, is a large value, it means that H0 is consistent with the data. So we do not reject it. And there's a higher risk of rejecting H0, right? And when it is a small value, H0 is inconsistent with the data, so we reject it in favor of HA. And there's a lower risk of rejecting H0. So intuitively, then the probability of mistakenly rejecting H0, given that H0 holds true, is small, it means that you do not have a very high risk of rejecting H0 because probability of mistakenly rejecting it was small, right? So you reject it, right? So when it is small, it would be easier for you to reject H0. And when it is large, the probability of mistakenly rejecting it is large. It is not very easy to reject. Okay, we will make it more clear. The action of mistakenly rejecting H0 given the test statistics while H0 holds true is called type 1 error. This value is actually called type 1 error. So we will talk about type 1 and 2 errors in the next session, but you just need to know that mistakenly rejecting H0 given the test statistics, while H0 was incorrect, that number is shows the type 1 error value. So what we want is that the probability of mistakenly rejecting H0 given the test statistics while H0 holds true is less than equal to our significant value. So what it means is that, let's say that our significance value is equal to 5%. So it means that then with 95% confidence, we can reject null hypothesis in favor of HA. Where does this 95% come from? Because confidence is 1 minus alpha, and our alpha is equal to 5%, right? So now we are saying that if the probability of mistakenly rejecting H0 given the test statistics while H0 holds is less than a small value of 5%, and we said when this is small, we can reject H0, right? So we can reject it with 1 minus alpha confidence. Okay, I hope it is clear. Okay, so the probability of x more than equal to x given that H0 is called probability value or p-value. So what it means is that in this scenario, we said that what we are discussing, our test statistics, x is equal to the number of cured people, right? So it could be, so we could be calculating what is probability of having 5 or more people given that H0, right? What is the probability of having all 6 people being cured out of 6 given H0, right? So these probabilities are called probability value, and we'll discuss it in the next slides in more detail. But here, as an example, we can say this, that if we said our small x to be equal to the number of cured people to be equal to 5, probability of x more than equal to 5 given that H0, if it is very small, we can conclude with 1 minus alpha certainty that HA is accepted. So what it means here intuitively means that if the probability of 5 or more people being cured while they haven't got any medicine is a very small value. So it is not really probable that out of the people who took the placebo, they will be 5 or more of them will be cured. It's very small. So it means that H0 can be rejected, right? Because obviously here, intuitively, the medicine has been impactful. So if that happens, and this value is less than equal to our alpha, we can say with 1 minus alpha certainty that H0 is rejected and HA is accepted, right? So the medicine is impactful. I think that intuitively makes sense, right? Take your time. Okay, so we will exactly calculate this value. We will come up with a certainty, and we will try different significance values in next session where we are talking about Fisher exact test, and it is very easy, but in this session, we're not going to cover that. Okay. So now let's move to the last problem of this session. And we're gonna calculate the exact p-values here. We're gonna accept or reject null hypothesis here. So let's say that we have a null hypothesis that says the coin used by judge in soccer games is unbiased, so probability of heads is equal to 1/2, and the alternative hypothesis says that the coin is biased, so probability of heads and tails is not equal to 1/2. So what we want to do, again, similar to the previous question, we are gonna design an experiment. So we flip the coin, maybe like 20 times, 100 times, or something like that. So let's go with 20 times. Then we can calculate what is the number of heads here out of 20. How many of them will end up being heads? Then intuitively, we might say, okay, if the number of heads is something between more than equal to 5, less than equal to 15, we are going to say that the coin is actually not biased, so we do not reject null hypothesis, we accept it. And if it is like more than 16, more than equal to 16, or less than equal to 4, it is not really probable that a unbiased coin will result in like 20 heads, right? So maybe there's something wrong with it. So we would reject the null hypothesis there. But this is very intuitive, right? So if we try this experiment many times, we might expect to see this distribution. This distribution shows how many times we will see the heads. Like you can see that it is, if it is unbiased, if H0 holds, this is the distribution that we would expect to see. We would expect to see that the number of heads and tails is pretty much the same, 10-ish, 11, 12, right? We do not really expect to see like 0, 1, 2, 3, or like 20, etc. Heads, right? So intuitively, what we are saying is that if the number of heads is something here between here and there, between 5 and 15, we're going to accept the null hypothesis. We are going to say that the coin is not biased, and if it ends up in either of these, we're going to say that this is biased. Okay, so but what this was very intuitive. But what actual range of x confirms the coin is unbiased? And let's say this is a serious thing. Let's say that is a serious game of soccer. So we need to make sure, and we need to have a confidence level here. And we want to know how confident are we. Let's say that FIFA wants us to be 99% confident about this coin not being biased, right? And they might actually do that. I don't know, but they might. Okay, so now let's go over calculating the probability of having 20, 19, 18, etc. number of heads using the information we already went over in the previous courses and previous sessions as well. So here I have number of heads. Here I have probability of these number of heads, given that I assume it is unbiased, right? So the probability of heads and tails is equal to 1/2. I can also show it this way. Probability of x is equal to x, given that x0, or I can just have it here. So 20 out of 20 means 20 out of 20, and there are 2 to the power of 20 different kind of like versions of flipping these coins. So it could be head, tail, etc. So you have 20 of them, and there are 2 options for each of them. That's where this comes from. It is 2 to the power of 20 in general, and 20 out of 20 are heads. And so we can calculate that. We can calculate like 19 case out of 220, etc. And I have already calculated those, and we can see that in the next slide, the actual values. And you can see that it's very unlikely that 20 out of 20 turn out to be heads, right? And what we learned was this, and you can see that it is like getting 14 heads is 3.6% probable, right? So, and you can continue this table. I didn't have a space, so I just showed some of them. So, and then we learned about this p-value or probability value, which was this value, probability of x more than equal to x, given that h0, or I can write it this way, probability of x given probability of, sorry, let me make clear. So it can be probability of x more than equal to x, given that h0. And these are equal. So what it means is here is probability of x more than equal to 20, given that x0. So this is this value. This is probability of x more than equal to 19. So I just sum up this and that to create this one. Here, that would be probability of 17, 18, 19, and 20. Probability of 17, 18, 19, 20, etc., etc. Right, and then probability of here, what it shows is probability of x more than equal to 14 given h0 is equal to 5.7%, right? Okay. So if we want to be, and then let's say that the FIFA says that our significance value needs to be 5%. So if you are 95% confident that this is not a bias, we will accept it. So now what we want to find is this value. What is this x here? Similar to the previous question, we want to know whether our x should be like 5 cured people, 6 cured people, 4 cured people, right? We want to find this x. Okay, so what is the x here? Can you think about it? What is the largest x and what is the smallest x? That would work here. Okay, so the largest x that would work here, probability of x more than equal to x, given that x0 holds true, is less than equal to 5%, would be 15. Why 15? Because this is the value that has the largest value, while the value probability of x more than equal to 15 given h0 is still less than 5%. So we're going to choose 15. And what is the lower, smallest x that we can say? And we will learn about these in the next sessions. But here, intuitively, if we think about it, you can see that the probability of having 5 heads is equal to probability of having 15 of them because of this. And so the lower bound is equal to 5. We will go over that in later sessions. But we found the range that this works. So if x is more than equal to 5, less than equal to 15, we accept the null hypothesis. Otherwise, we will reject it. So if you think about it, it's basically in this distribution that we have, it's what we calculated was this value. We calculated the area here. The probability of this part was less than 5%. And this part together, like 2.5 almost, right? So probability of, so this shows probability of h0 is more than equal to 15, right? Okay, so p-value, probability of x more than x, given that h0 holds true, it's got p-value of x, and is the probability of observing value x or more extreme values of x when h0 holds, right? Okay. And obviously, if you think about it, if this probability is high, so it means that, let's say that if this was high, for instance, let's say the probability of observing 17 or more was like 8%. So if we observe 17 heads, we couldn't easily say that it is not biased, right? We couldn't say that it is biased, right? We couldn't easily reject null hypothesis h0. But since it is not really probable to observe 17, 18, etc., it has a very low probability. This value is very small. We can easily reject the null hypothesis if we observe 17, 18, etc. number of hits, right? Okay, so another example is that if the p-value is set to be 0.2, it means that you could observe 15 heads with a 20% probability, and we cannot very easily reject the null hypothesis with x is equal to 15, right? You can, I would suggest you to do the same problem that we did with x with significance value of 1%. So let's say that the FIFA wants a confidence of 99%, right? Okay. So in conclusion, if significance level is pure 5% and p-value is less than that, meaning probability of x more than equal to x given that H0 holds true is less than 5%, we can claim our results are significant results and we can reject the null hypothesis H sub 0. Okay, so as always, we have an exit ticket, which is a simple multi-option question with unlimited attempts that you can find in Canvas, but you can also scan here and submit it for extra points. And for the homework bonus question, I would like to ask you to design a hypothesis of your choice and to test whether it holds true or not. It could be about election, for instance. You can ask people, and for asking people, we have this criteria that you can find in more details. And also another example could be this A/B test of software. You can for gathering the data, you could ask people whether they prefer one or the other interface or something like that. It is your choice, and it has bonus points. It's not mandatory. And for next session, we will have today's follow-up, hypothesis testing using feature exact tests and simple obvious complex hypotheses. We will go over z-tests. You can find the code in the GitHub. You can work through that. We will have t-test, type 2 error, and then briefly relating this to machine learning, we'll go over sensitivity and specificity. Thank you so much. If you have any questions, please let me know. Send me an email, and I'll see you. Thank you.